Welcome to our video series on Fooled by Randomness. This is the second video in our series, and in this video we are going to cover an explanation of the Monte Carlo machines that are mentioned inside of the book. So, in Chapter 3, Taleb introduces the idea of using Monte Carlo machines. He describes Monte Carlo as creating an alternative history or an alternative sample path that is different from reality. In other words, Monte Carlo methods are a broad class of computational algorithms that rely on repeated random sampling to obtain numerical results. They can be used to solve any problem which has a probabilistic interpretation. So now let's look at some of the mathematical uses of Monte Carlo simulation. So suppose we have an integral, g of x and f of x, where f of x happens to be a PDF, meaning that it integrates to 1. This is like saying that we want the expected value of g with respect to f. So what we can do with Monte Carlo is generate x1 through xn following the distribution f, and then take g bar as the sum of the g of the xi's and divide that by n. So this, actually, if the expected value of the absolute value of g with respect to f is less than infinity, then g bar converges to the expected value of g with respect to f as n approaches infinity. So our estimate is useless unless we can see how precise it is. Now luckily, with Monte Carlo, we can actually do this due to the central limit theorem. So we have this equation right here, and what it boils down to basically is that the standard deviation of g is equal to the variance of the g's of the xi's. And it can be estimated with sigma hat n, which is equal to a classic standard deviation equation. And we can then use a classic confidence interval equation to get a confidence interval for g bar. So now we can look at a real simple example. Consider the integral of e to the x from 0 to 1. We can let g of x be equal to e to the x, and f of x can be a uniform 0, 1. Then our integral would look like e to the x from 0 to 1 with an indicator function for indicating if it's a 0 or 1. So what we can do is simulate xi equal to x1 through xn from the uniform 0, 1, since that's our f, and then let yi be equal to e to each of the xi's. But then what we could do is take the mean of our yi's, and that will give us our estimate for this integral. Now we know since this is very simple, this estimate should be very close to e to minus 1. So now let's take a look at this in R. So we can sort of see the true value of this integral, exp minus 1. So you get 1.718. So that's what our goal will be for this estimate. So first off, we generate uniforms. I'm going to generate 10,000 of them, and they go from 0 to 1. And then we just let our sample y be equal to the exponential function of the u's that we just generated. And now we could take the mean of these y's, and we get g bar is equal to 1.72, which is very close to our estimate. And now we're going to get a confidence interval for this to see how accurate our estimate is. So we calculate the standard deviation of our y's, and then we just use the simple confidence interval equation. And we get a very good looking confidence interval with very small margin of error. So now we look at a very simple example that relates to the book Fooled by Randomness. In the book, Taleb is always talking about how people are constantly checking their stocks and they're feeling many emotions when they go up or down. But really, these stocks are changing just due to random noise since they're checking on like an hourly basis. So what we can do here is run a Monte Carlo simulation. So we don't always have to be doing like an integral or something to use this powerful tool. Really, all we need to do is run a simulation, and then we could take a sample statistic. So let's say that in a day, there's a 0.49 chance that you lose $1 on an investment, and a 0.51 chance that you gain $1 on an investment. Well, we can simulate a day's results by sampling a -1 or a 1 based on these probabilities. And now we'll check it out in R. Alright, so we're going to start off by making a vector that is just the -1 and 1. We call that gain. because you're losing $1 or gaining $1. And now I'm going to set the seed so that we can get the same result every time. And we're just going to sample a week's worth of losses or gains. And now we can take a look at this week. So looks like we have 4 losses and 3 gains. So the mean of this week would be negative 0.14. Now the way the probabilities are is that you should be gaining overall, but in this week we just happen to get unlucky. So now what we're going to do is look at a year's worth of samples. And here we are going to not look at all the samples at once because it's so many, but we will look at our mean week or our mean year. And what we do when we get that is see that it's a 0.101 gain overall. So that makes sense with our probabilities, since we should overall be gaining throughout a year. And we can get a confidence interval once again to see how accurate that is. And it looks like we can be very confident, 95% confident, that we are going to gain in a year. And that is going to be it for this video. As Taleb stated, we can see that Monte Carlo is a very powerful tool, and I hope you have a better understanding of it now.